Hey, good morning, everybody. So today is our last class, and our last topic is recurrent neural networks. So how we work with time-dependent data. Um, so let's think about like a concrete example when we want to process text, because in words, the order of characters is not arbitrary. It depends on the previous um, characters. And in text, the next word also typically depends on the previous words. So how to keep track of this kind of previous history dependency? Um, so if you think about a, um, a word, or then we can encode the either on character level or on the higher word level. So we can create dictionary for the words, so we can create dictionary for characters. And of course, the dictionary for characters will be much smaller because we have just about 50 characters if we count uppercase characters. And if we work with words, the dictionary of words, do you remember how many words are in English language? About 300,000. So if we work on the word level, then our dictionary size will be much larger. Anyways, how to encode one element of our dictionary? Character or the word, which methods do you know to encode items like categorical data. But so did I teach you how to encode categorical data? One hot encoder is the easiest way. Yes, and the other way, I think we didn't talk about this. To create, Torch has embedding layer, and embedding layer will just initialize the metrics with embeddings. I think I have this example in my code. I will show you. But instead of using just zeros and one for encoding one character, we can use a vector with real numbers. And then for one code encoder, we should have the size of this vector the same as the size of the dictionary. If we use a real number encoding, we can use the much smaller shape of the encoding vector, because with real numbers, we can encode much more information than with integers. So the X will represent the encoded vector. If you think, if we uh, think about words, then, for example, yeah, like we have a name, for example, and we have a dictionary. And then we create a one-hot encoder. And then A will be represented by a vector like this. L will be represented by a vector with one at the index for L, and E will be, well, if we use non-integer encoding vectors, then maybe A will be represented with some, I think it would be enough vector just of dimension 5 or 3 instead of the entire dictionary length to include all the characters and so on. So, and we will denote this vector representations of the characters because we can work only with numbers by x1, x2, and so on. So this will be, in this case, x4 and x5. So this will be the representation of our name. So it will be represented by a tensor of shape the size of our dictionary times the number of characters. And so this is what I denote by x1 and x2 and so on. So this is the input sequence. You also can think about time series, like then x can be one-dimensional if you want to predict just one-dimensional data. Yes?
So X is the input, and H is the data of the time.
No, H it's a hidden state. So X are the embeddings of data.
The H in this case is the hidden state of the
Yeah, I will talk about the architecture later. Yeah, the X is the matrix array of vectors or of numbers if it's time to one dimension. Yes, but typically we have vector representations for every element of our sequence. So now we will so as I mentioned in the beginning, we want to keep when we process the next token, sometimes abelians we call tokens, we want to keep track of the previous embeddings. So how to keep track of the previous embeddings? We can you can think about the following model. So we will initialize somehow the vector h0, which is h because we call it hidden state. And so this model is similar to hidden Markov chains, but hidden. So when we don't know the real values of our data, of our random variables, and we also can observe our data, and we want to figure out something about the real distribution behind the data. So, and typically, we will denote by the circle one cell of this neural network, and it will take two inputs, the hidden state and the first embedding, the first character, for example. And then generate the next hidden vector. So typically, yeah, we write the next hidden vector here. So H1. So to generate the next hidden state, we will use the following formula. We will take the input X and apply just linear function to this X. And also we will add the, so for the first vector, you can initialize this vector just by zeros. We will add the another matrix. So let's denote this matrix with subscript X. This matrix is superscript H times H0. Plus bias. Plus bias. And it's important that the output dimensions of these matrices are the same. So X and H, they can have different dimensions. For example, H can have dimension 1000, H can have dimension 100. But if we apply our matrix of the shape hidden dimension times X times input dimension, and this matrix of the shape hidden dimension times hidden dimension, then the result will have the dimension of the hidden state, and we can add them together. And V has the shape of VH. So on the next step, when we reduced the next hidden state, we will use the new generated hidden state as input to our recurrent cell. So on the next step, we will use as input X2 and H1 as the hidden state. And then we will calculate the new hidden vector H2 by the formula, similar formula, but now instead of 1, we will have 2, and instead of 0, we will have 1. So the general formula will look as follows. Some matrix times input plus bias plus some matrix times hidden state input plus previous product bias. And then we also apply non-linearity activation function. And because these biases have the same dimension, we can just use one bias term. In practice, we typically concatenate these vectors. Why we will actually keep the information about the entire sequence? Because when we calculate H2, we will take into account previous vector x1 and h1. When we calculate h3, we will take into account x2 and h2. I think I have a mismatch. Let's see. Oh, no, no, sorry. For h3, I will have input x3 and h, but h2 has information about x2 and also about h1, and h1 has information about x1. So it means that at this step, when we calculate h3, actually we will have information about all previous input specs. Does that make sense? It's kind of a recursive formula. And the last observation is that instead of using two linear layers, so it's just a linear layer. How we implement this? Just apply linear layer. Instead of using two linear layers, we can concatenate these matrices and see if I have this on the next page or not. Aha, yes, I have it. So, and finally, when we reach the last token x, t capital, through ht minus 1, we have information about x minus 1 and all previous x's. So we hope that the last token contains the information about the entire sequence. And for later, for example, if we solve a classification task, for example, in my code example, we will predict the country of the origin of the name, and then it will be classification task. For classification task, we will take only the last hidden output and apply linear layer, from the shape of the x to the shape of the number of classes and cross intervals. So now about optimization of our formula. Instead of using two linear layers, we can initialize one linear layer. It will just save a little bit time for computation and concatenate these vectors x and h. And then this matrix W will be the concatenation of the matrices Wx and Wh. Because if you multiply this by concatenation of x and h, you will get exactly this sum. I hope it makes sense. Yes?
Yes, it's just making matrices out of matrices, basically.
Yeah. We just, so W is just taken of two matrices, but in code we will just initialize a large matrix and apply it to the stacked vector of examples. So instead of initializing two linear layers, we can initialize one. It's just for efficiency. Okay, now the main problem, vanishing gradients. So we talked about how we can solve this problem last time. Do you remember how to solve the vanishing gradient problem? Uh, we talked about ResNet. ResNet use this residual connections. Yes, just
Dropping out nodes that may not, that just don't do anything.
this is regularization of neural networks. It's a little bit different. If you want to solve the vanishing gradient problem, last time we talked about skip connection. When we use output from one layer and add the output from previous layer. And now, so with recurrent neural networks, there is also this problem with vanishing gradient, because if we calculate the derivative, it's important to understand that when we calculate the next hidden vector ht from x and h, um, we will use the same matrix WX and WH. So we initialize only two linear layers and we use them on every time step. So even though we draw different circles, but in these circles, the parameters W, X, and H, they are the same. They are shared between all these nodes. So that's why also sometimes recurrent neural networks are um, uh, represented as well as like circle, because it's kind of we pass X and H through the same linear layers, but we use new X and new H every. So to calculate the derivative with respect to our parameters, for example, W, we should first calculate the derivative of loss with respect to the last H. Then to calculate the gradient of the last H, we should calculate, oh, it's here, the derivative of the last with respect to the upper last, and so on, until the first H line, until H1. Because H0 is just initialization. So if the sequence length is, let's say, your word is, well, the word can be 50 characters long, but if you think about sequence of time series, for example, then of course it can be very long, and we will multiply gradients the same number of times as the length of our sequence. And if our sequence is long, we can run into this problem with vanishing gradients. So typically, after the length of 20, like 20 axis, this architecture will forget the previous axis. And also, there is another modification of recurrent neural network, which is called LSTM, long short memory, which kind of introduces another cell state that helps to process longer sequences. If we have time, we will talk about this. Okay. So this is just a reminder how we can solve vanishing gradient problem. Initialization, batch normalization, dropout also is regularization technique, but batch normalization helps with vanishing gradient problem because it normalizes the layers. Yes.
Would also work if you just normalize the gradient, if you calculate like an intermediate gradient and then normalize it and then calculate the next gradient and normalize that, or would that be like a bad idea? Or like would it like would that accidentally change the direction of the gradient? In that case.
Well, batch normalization actually, yeah, that's this normalization, but um, um, but kind of mathematically we want to get the true value of gradients. So if you so for example, if your input is one-dimensional, the normalization of gradient will always return gradient of equals one, and every time you update your weight, you will update by the same gradient rate times one. So it's maybe not a good idea, but
Is there a way to modify it though, to just simply produce three, I guess, different-ish gradients to just like make, and then put it into the loss function, and you just choose the best one that's closest to the smallest or that not like required.
um, I don't know, but if we can calculate the true gradient, we maybe would prefer to calculate the true gradient. So, and for example, if we add this uh, skip conversion, we can calculate the true gradient. Okay, so this is LSTM. Before talking about LSTM, let's look at the example. Okay. So in this example, we will work with data set of names and countries. And we will try to predict which name actually has origins at which country. Where is the data? Names, okay. So this is how the data look like. We have now folders and for example, in folders we have files like Arabic contains the Arabic names. Czech contains Czech names. French is the problem because it has some accents like here, and if we want to use just English characters like ASCII code dictionary, then we will need to say to replace this character with the standard E. So I create the dictionary of letters and also add this punctuation. Actually, maybe we don't need the punctuation. Um, then we convert to ASCII code our um, this is the function that will convert to ASCII code these names. Do you remember what is the default encoding system in Torch? Um, so it's UTF-8 when we use 8-bit for simple. But of course, it extends if needed. So finally, we create the data set. Um, so, first I create a dictionary, and dictionary returns just the name and the country. For example, 100 returns this name and the country and so on. And this will be our data set. Like name is the input features and country is the label, the target. Also, I created the dictionary of countries because we will convert countries into classes. Um, and finally, this is the data set, which returns what does it return? It returns um, why is it 5 times 57 shape? So where is our real name? I believe so where is my dictionary? Data. Mhm. So my first element in my data set has this name and this country. So the name has 1, 2, 3, 4, 5 characters. Then these characters are transformed into one hot encoder vectors. And because my dictionary has 50, this has 57 elements, this name Havana will be represented by a tensor of this shape, 5 by 57. So 57 is the size of the dictionary, and 5 is the number of axes. Okay, we create data loader. The problem, let's see again. The problem with sequential data is that they have different length. So we can't concatenate the name with 5 characters and name with 6 characters. So there are different approaches. We can either cut the longer sequences or add zero span smaller sequences. Just to avoid this problem for now, I'm using batch size of 1. So I won't run into this problem that we have different uh, um, shapes. Okay, now our model. So as I mentioned, we will use just one matrix instead of two. So I create a linear layer of the double size, input size and plus hidden size, and output shape of hidden size. And a final linear layer from the hidden size to the number of classes, the number of countries. I mean, this is just our uh, implementation, but of course, later on, we will just import, call the RNN layer from Torch with their built-in layers. So in forward mode, we initialize the hidden state H0 by 0 initialized. Then uh, for the length of our sequence, we apply this formula. So we apply linear layer to concatenation of X and H. And well, in my formula, I use X and H, I believe, but here with H and X. Okay, it won't confuse you, and then apply nonlinearity. And after we iterated until the last character, we apply a linear layer to the hidden vector H, to the last hidden vector H. Okay, let's run this. So I initialize the input. So 57 is the size of X, the input, and 100 is the dimension of the hidden state of H. Okay, cross entropy loss and the standard training loop. Um, so sometimes you will see optimizer zero grad before backwards. And maybe it makes more sense. But if we initialize our model and then immediately begin training, then the model will have nuns, like not initialized gradients, so we will have empty gradients. But uh, yeah, if you want to be sure that you begin optimization with zero gradients, then maybe it's a better idea to use optimized zero grad before calculating the loss. Well, but actually, loss was also defined before. So just sometimes you will see optimized zero grad before the back propagation. Okay, let's see the accuracy. Because we use gradient descent, it's stochastic, so accuracy can change from one uh, training to another one. Okay, and if we want to get the prediction now, for example, um, actually, I'm doing here. So I apply my model to X. It returns the what is the number of countries? Let's see. So uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it's easy just to type shape. We have 18 countries, And the model predicts 18 numbers. Then we apply softmax or just argmax because it doesn't matter if we take maximum of logits or maximum of probabilities. And we get the prediction. And yeah, sometimes prediction is incorrect. Sometimes it's correct. So this is how the recurrent neural network works. Now let's do the same, but with a built-in function. The built-in layer, recurrent neural network layer. So it has the input size, the x, hidden size h. By default, for some reason, the input shape by default is the length of our sequence, not the batch. If we want to have the batch as the first dimension, we should indicate this parameter batch first equals true. Then if batch first equals true, the first dimension will be the batch size, the second dimension will be the length of number of x's, and the last dimension will be the hidden shape. So instead of all this code, I will use only this code. So we apply RNN layer, and it will return two values, out and h. So what is that out? The out will be the list, well, it will be tensor of all vectors, of all hidden state vectors, beginning from h1. So this is out. The h will be only the last hidden vector from our sequence. And because for our task we will use only the last one, So I'm using the last vector of the out. And yeah, you can see how uh, less code we should use with built-in RNN function. And we can initialize, and it will work perfectly. Or what? I commented one line. I need out. Okay, now because we have time, I can talk about the modification of this RNN layer, the LSTM layer. Oh, and also I have embeddings. I want also to show this embedding layer. So let's maybe play with it first. So instead of using one hot encoder. So um, to use this embedding layer, we don't need to create one hot encoder representation. We just need to initialize the parameter, the number of classes. In our case, it's the length of dictionary. So I should change a little bit my data set. Because for now, my data set returns tensor 5 by 57, but because embedding layer will create actually embeddings for us, my output should be just 5, just different characters. So how can I modify my data set? So I think I should use this one. Let's see. Yeah, so now um, my data set returns just the indices of characters instead of embeddings, instead of vectors. And I can just pass this into neural network directly with this embedding layer. In embedding layer, we initialize the embedding layer with random numbers and indicate the dimension, the number of classes, in this case, the number of characters, and the embedding dimension. So instead of like in one hot encoder, we had dimension 57, here I'm using dimension 16. I could use also 5. I believe it's enough to encode 57 characters. So, and in my forward, I will need to apply encoding. So first, before applying RNN, I will need to apply this embedding layer. So embedding layer will convert just these numbers, the indices of characters, into vectors. So let's initialize this model, and here is the example of this embedding layer. So for example, my input x is just this set of integers, but after applying embedding layer, every integer is transformed into a vector of size 16. And now we have this tensor. Like before, we had a tensor 4 times 57 and used as input to recurrent neural network. Now we will have tensor 4 times whatever dimension we indicated in embedding layer. And as you could see, this embedding now contains just some real numbers instead of one-hot encoder vectors. And neural networks work better actually with real numbers than with integers. So it's the standard practice to use embedding layer instead of one-hot encoder. Okay, and then we can train our model. Um, so something, I should also change something with my model. Uh, so yeah, I should use 16 now. Because after embedding, the input shape will be 16. And believe me, the accuracy should improve. What was the previous? It was something about 70%. And just because we used real numbers for embeddings instead of one-hot encoder, even though and also the small dimension, but still, I believe it should work better. Okay, while it's training, let's take a look at the LSTM layer. So one iteration is called recurrent neural network cell, RNN cell. The entire sequence, this for loop, is called RNN layer. The same with LSTM. Now we will look at one step, LSTM cell, but when we apply this to the entire sequence, then it's called LSTM layer. So, in recurrent neural network, just for comparison, we didn't have this upper path C, which is called state cell. We only had the hidden state H. And in vanilla recurrent neural network, we just so we didn't have all this part. We just applied linear layer to kind of blended this x and h and applied sigmoid function, and this was our output. So kind of only the bottom line is the RNN. Oh, actually, it's stopped training. Let's calculate the accuracy. Hmm. Mm, I don't remember what was the before that. So it's hard to say if it's improved, but um, I believe it should improve. So now let's look at all these parts in details. Well, currently, of course, people use transformer models for sequential data, but some applications like in translation from one language to another, at least 1 year ago, still in Google Translate, the uh, recurrent neural network-based architecture was used. Mm, So, in LSTM cell, we have additional inputs. Additional inputs also get translated. So now we'll have two inputs in addition to our X. And the you remember the problem was with vanishing gradients. So kind of forget the information from about 20 steps uh, before. And so to keep this information, this state cell, like long memory, this is short memory, this is long memory, was introduced. Now let's understand how it works. Um, so we have an option to pass our uh, input hidden state vector H directly. So this is I. Yeah, I represents the formula from recurrent neural network. I, because of information, we pass the information. But we also introduce gate. G stands for gate. And gate, so this segment actually denotes the hyperbolic tangent function. It's not a segment, it's hyperbolic tangent. It just stands for some oscillation. Uh, and this G stands for actually sigma. And sigmoid function, you remember it takes values between 0 and 1. So sigmoid function takes values between 0 and 1. So we introduce this additional linear layer. And this additional linear layer can result in small values or in large values. If it results in small values, we will get, after applying sigmoid function, something close to 0. And when we multiply this output from the standard output from recurrent neural network with gate, if gate is close to 0, we kind of will cancel this signal, this input. if this linear layer will take high values, then after sigmoid function, we will have a number close to 1. And multiplication, this dot stands for multiplication, will actually result just in this value I. That's why it's called gate, because depending on, on, on these values, large or small, we will multiply our output either by 0 or by 1, well, maybe by a number in between 0 and 1, but this is the why they call this gate. And after that, we take information from the self state, previous, and add the information from the current x. Again, if our gate was 0, we kind of won't add this information from the current x value. If gate is close to 1, we will add the information from the current value x. And also they introduced gate for the so what out. So out also looks the same as in the recurrent neural net. That's output like from vanilla recurrent neural net, and we multiply this also by the gate. So if gate is close to 0, we won't use information from H. We will use only information from C. If gate is close to 1, we also will add information from the current value of x. But this gate, you can see the gate is controlled by cell state, gate of C. Kind of this long memory will decide if we should pay more attention to the input signal or to the actually information from the previous cell. And there is one more detail. What's the name for this F? So F stands for some rot, I don't remember. But the idea, forgetting gate. F stands for forgetting. So actually, yeah, so we also can multiply the long memory C value by F, like just in the input into our into our cell. Again, if F is close to 0, we will actually forget the history from the previous cell in the long memory. And this is this schematic. So now I think this picture will make more sense for you. So this is the forgetting gate, like blending x and h, applying sigmoid function, which is between 0 and 1, and multiplying with input signal from the long memory cell state. This is the kind of information grading. I with hyperbolic tangent activation times gate with sigmoid activation. And we add this information to the long short memories. So we kind of incorporate the information from the current X, like from short memory, to the long memory, that's the state C. And again, we can erase the previous memory with this target and gate, or we can keep the memory for the long state. And this line is just the standard RNN output, but again, when we multiply this with this um, um, is it tangent? Um, I was thinking that that was a sigmoid function. But anyways, this is kind of blending of the standard output from recurrent neural network with information from the long memory. So this is the idea of LSTM. And because of this gating mechanism, it can process longer sequences, like up to 100 or 200 element sequences. And let's try to apply this to our model. Where is it? So now, so a LSTM cell has a little bit different parameters, and then LSTM. Yeah, there is tangent. Okay. Um, so it returns the hidden vectors, but also it returns a tuple with last hidden state and last cell state. So in RNN here, there was only H, now we have a 2. But because I don't need to use this hidden state for now, I will just skip it and use the last hidden state. So let's try to use LSTM. Hidden size 32. Let's try hidden size a little bit larger. And I'm not using GPU if I will, but because I'm processing just one name at a time, which side is one, actually, I think I wouldn't have any reasonable time improvement if I would use GPU. Okay, while it's training, I want to show you how it's applied for example, translation from one language to another. one. Um, oh, sec to sec. So, for example, if you want to translate from one edge to another, you create two recurrent neural networks. One will work with tokens from one language, another will work with tokens from another language. So you take the last hidden vector from the first neural network as input as H0 to the second neural network. And it will, even without attention, it will perform some translation. Well, not perfect because it's the easiest architecture, but still like this. Um, some phrases are correct. Because with attention and transformer models, it works better. Okay, let's look at the accuracy. And we will stop here our course. Um, so, yeah, you can see the accuracy improved. Um, yeah, thank you for taking this class, and I wish you nice end of this term and nice break. And so let me stop recording.